This is section 5.3, the Fundamental Theorem of Calculus. Here's where we relate the derivative and the integral, and more importantly, learn a way to find the exact area under the curve without having to do all of those crazy limit techniques.
They're different.
Consider this problem, problem 1. Pause the video and read it. Now recall that distance equals velocity
It's different.
times time.
I know, it is.
Since our velocity might vary, we have to take many
Okay.
velocity times time products. And just to illustrate what this means, we might have something like this. And we've got some sort of a curve going on here. Maybe this is from A to B. And maybe we just divide this into little intervals like this. Pretend these are all of the exact same width.
Daddies don't even exist.
And then let's suppose, so we say, okay, let's approximate this with that velocity. Of course, it's an approximation, but we're just going to do that. And then I guess we could do this. And then we could do this. And this. And this. And this. And you see how we can just sort of keep, hold on a sec. This, and then this. And we could just sort of keep doing this. All right? And so each of these is a certain velocity, call this like V1, V2, etc., at a certain time, right? A could be like T1 and T2, right? And so what we could say is that the position, or the total position that we've covered, is just velocity 1, actually really what this is, each of these is a delta x, right? That's the amount of time that's elapsed between this time. So we could say that, you know, the total distance, or maybe I'll say the net distance, or displacement, equals v1 times delta x plus v2 times delta x plus blah, 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 and then if this is vn, plus vn delta x. Okay? Does that seem familiar at all? Well, if you think about it, these are really just, you could think of these as just rectangles, right? And we're just finding the area of these rectangles, just like we did before. So I'll say C section 5.1. So we know that the total distance traveled between times A and B, just by the definition, is the integral from A to B of, if this is, you know, y equals f of x, or I'll call this f of t, I guess, really, just for time purposes, right? The integral of f of t dt. That's the definition. But we know that the velocity function is the derivative of the position function. So if the position function is f of x, we could say, well, I guess, I guess if I call this v of t, right? Because if this is the velocity function, I should say, right? Then the integral from a to b of v of t dt equals the integral from a to b of, I guess we could call this s prime of t dt, where s prime of t, or s of t, is the position function. Position at time t. Okay. I.e., what this really means is that if we take the derivative with respect to x of the integral from a to x of s prime of t dt, this is going to equal s prime of x. Okay? So what this means is that the instantaneous velocity of this guy is v of x. Just to be crystal clear. So this is the fundamental theorem of calculus part 1. It says that if we have the function f of x defined, this is a little technical, the integral from a to x of little f of t dt, where x is ranging from a to b, then the derivative of this guy with respect to x is just plugging x in for this guy. Okay. All right, and then the fundamental theorem of calculus part 2 says that the integral from a to b of f of x dx equals big F of b minus big F of a, where f is an antiderivative of little f. Okay, so to find the definite integral of a function, we anti-differentiate, move that over a little bit, and find f of b minus f of a. Okay, so let's just do a bunch of examples at this point. All right, remember that problem that we worked so hard to show that it was 8/3? Well, let's see if we can do this a bit quicker now. We know that antiderivative of x squared is 1/3 x cubed, and then this is the notation. We draw a vertical line, write the upper end point above, lower end point below, and we just say, okay, this is going to be 1/3 times 2 cubed minus 1/3 times 0 cubed. We do it out, and we get 8/3. Well, that took a little bit less time than before, right? So that's what we do. Let's try this guy, example 5. The integral from 1 to 3 of 5x to the 6th minus 4, we do write that dx, that's part of the notation, right? It's going to be 5/7 x to the 7th minus 4x from 1 to 3. This is 5/7 times 3 to the 7th minus 4 times 3 minus, and then just be a little careful here, right? Put this in parentheses. 5/7 times 1 to the 7th minus 4 times 1. And you could simplify that if you want. Okay. On the flip side, right, that was FTC2 right here. Just want to point out that was the second part of the fundamental theorem of calculus. FTC1 is right over here and here. Let's do a couple of those, right? To find the derivative of this function, all we do is we check to make sure that x is on the top of the integral, which it is, or the top upper bound, and we just plug it in for t, right? Because that's what FTC1 said. Now, in this case, we have to be a little careful, right? Because g of x, wait a minute, because g of x, it equals the integral from x to negative 5. We need the x in the top. So really that's negative the integral from negative 5 to x of 1 plus t to the 7th times t to the 6th. Right? Because when we flip the bounds, we flip the sign. So g prime of x equals, let's see what that's going to equal. 1 plus x to the 7th times x to the 6th. Okay, that's it. All right, let's do a couple more examples. This integral right here, let's actually get rid of this right here. That's going to cause us problems. So we're going to get here the integral from negative 4 to 1 of cosine of x plus x to the 4th minus 9x dx is going to equal sine of x plus 1/5 x to the 5th minus 9/2 x squared from negative 4 to 1. And so we just plug this in. This is not going to be a nice answer, by the way. minus, and then do the same thing, minus 1/5 times negative 4 to the 5th. And then just be careful, right? We're flipping signs. This is going to be 9/2 times negative 4 squared. But you see how that's a plus? Right? It's a plus because this is a minus. So just be careful. The signs always flip. Okay? One more, slightly more complicated example. Because we have an x term in the bottom and an x term up top, we have to be a little creative. And from the integral property number 3, we have to rewrite h of x as the integral from 1 plus sine of x to 0, sine of t to the 6th dx, plus the integral from 0 to x cubed minus 4x of sine t to the 6th dt. Oh, I said dx here. I meant to say dt. So the derivative is going to equal, so first of all, we know that we could just swap these guys, right? And make the whole thing negative, right? So actually, you know what? Let me not do this. So implies, I'll just write another equal sign because we need to be a little more careful about this. This is going to be, let's do a little copy paste though. Here. And we're just going to swap these bounds right here. 1 plus sine of x, 0, and we're going to make that negative, right? You see the difference? So h prime of x is going to equal, I guess it's negative sine of, oops, you know what? I realized, sorry about that. I forgot to put a negative sign in front of that. Sorry about that. Over here, didn't forget this time, negative sine of 1 plus sine of x to the 6th. And then we need to use the chain rule and take the derivative of the upper bound. Okay? And then same thing here, right? We're going to have sine of x cubed minus 4x to the 6th times the derivative of x cubed minus 4x. Again, we're using the chain rule right here.
Sounds different.
And that's what we've got.